next speaker is Katelyn Greene, a bioengineer from University of California, Berkeley, working on a PhD at Virginia Tech, talking about assessing crew member health and long-duration spaceflights.
So good afternoon. It's such a pleasure to be here with you all today. Thanks for having me. The talks so far have been absolutely fascinating to me. It's not my background, from solar sails to terraforming our destinations for long-term inhabitants. You all have really opened my perspective to really how we're pushing the frontiers of spaceflight now. But what we haven't discussed so far as much is a limiting factor of interstellar travel, the physiology of the human body. So, you all likely know from extensive media coverage over the years that the absence of Earth's gravity causes bones and muscles to deteriorate. However, we still don't understand exactly where the most extreme deteriorations occur and how these may accumulate to become detrimental to crew member health. So our research brings together the worlds of biology and engineering to specifically study and predict how bone and muscle changes occur in the spine and how this will affect crew member risk of strength and injury. So with that, to start you on this journey, let me orient you to what we already know about bone and muscle in space. From the last 6 decades of space travel, we know that extended time in microgravity changes both the cellular and macroscopic physiology of the spine. So this means that without terrestrial gravity, the muscles that support the spine are no longer being used to maintain an upright posture or do normal locomotion. So these muscles rapidly get weaker and they atrophy. You've probably heard the term, if you don't use it, you lose it. It's similar to that. And when we consider bone changes, it's important to know that bone actually grows in response to mechanical stress. So in space, the bone no longer needs to resist the constant mechanical load of gravity, and this disrupts bone metabolism, which means that bone effectively will break itself down faster than it can build itself back up. And over time, this leads to weaker, more porous bones like you see in the top picture up there. And so what this means is that on a typical 6-month mission to the International Space Station, astronauts will lose up to 15% of their muscle and bone mass in critical regions like the spine. And 15% is certainly an alarming number. To put this in perspective, this means that 1 month of space travel causes losses that exceed 1 year of losses in high-risk populations on Earth, like postmenopausal women. And this is important for us to consider because these losses lead to chronic conditions like back pain, disc herniation, as well as even vertebral fracture. And so you're probably wondering why this matters. So all this biology matters for interstellar travel. We've talked a lot about that a journey to the stars is not going to be a short-term flight. It's going to take years and generations to reach our destinations. And because all of our reference biological data is from 6 to 12-month missions on the International Space Station, we simply don't yet know how these changes are going to manifest at larger timescales. If left unchecked, these changes may aggregate over time and leave our interstellar travelers too weak and too frail to conduct extravehicular activities that are necessary, as well as do surface explorations. So severe injuries, especially in the spine, may compromise entire exploration missions. So to address these concerns, our research group is using computational biomechanics to study how long-duration spaceflight affects vertebral strength and injury risk. We're currently conducting an ongoing study with NASA. There are 9 astronauts in our study that are on 6-month and longer missions to the International Space Station. And with these astronauts, we're gathering biomedical imaging before and after spaceflight. So we're getting magnetic resonance imaging, which is better known as MRI scans. And then we use that to look at soft tissue. And we also gather computed tomography scans, which are known as CT or CAT scans. And we use these to look at bone health. So together, we can gather how bone health and muscle health are affected by spaceflight. We can look at bone mineral density, which is how porous the bone is throughout the spine, as well as the thickness of the outer cortical shell of the bone, which we know contributes to vertebral strength. We can also look at metrics of muscle health. So this may include muscle size, like cross-sectional areas, as well as volumes, and can include muscle quality, which in our case, we're looking at how much fat tissue is in the muscle, because we know if there's more fat tissue, it's going to compromise the structure of our muscles. And so with that, just here's two examples of the types analysis that I do on a daily basis. So in the upper neck region, I have an example of a muscle size measurement. So when I look at a scan, first I need to outline the location of all the muscles, and this is what I call a segmentation. And to take an actual area measurement, what I can do is take the area of one of the little squares in the image, which is known as an image pixel, which you guys might be familiar with, and then we multiply that by the number of pixels that are in my outline segmentation, and that gives us a measure of muscle size. And then for muscle quality, I have an example in the lower spine, and I'm looking at muscle fat infiltration. And again, you can see in orange over there, I have a segmentation of the paraspinal muscles in the lower back. And on the far left, you can see I have a small red square, which is actually a fat reference point. So then I can extract the mean pixel intensity of the muscle and compare it to that of the fat reference, which gives me a general idea of a ratio of how much fat is actually in the muscles that I'm looking at. And so we don't yet know from our ongoing study what the results are going to be, because it's still ongoing. However, I can share with you some preliminary data that we've just wrapped up from basically some retrospective studies that occurred over the last couple of decades on the International Space Station. And with that, what we found is that there were actually size increases in the neck area, so in the sternocleidomastoid, and the semispinalis capitis, and the trapezius. And at first, this may seem counterintuitive, right? I've just told you we expect muscles to actually get smaller with space. But if we look towards the function of these muscles, they're collectively responsible for the flexion and the extension of the neck, which is like the yes and no motions, as well as like the tilting of the neck, which we know are required for nearly all everyday activities on the International Space Station, perhaps more so than that would be used here on Earth. So we may actually expect these increases. And then in the lumbar spine, we see decreases, which are decreases in the paraspinal muscles and the quadratus lumborum muscles. And these actually would expect, because these are anti-gravity muscles. So without gravity, they're not being loaded. And again, if you don't use it, you lose it. So they're getting smaller. And the results of these two regions have recently been published in Frontiers for Physiology in the last few months. And in the next few years, I'll be able to present more on what's going to happen with the astronauts that are currently on the International Space Station. And so overall, though, we have to be really careful in interpreting size change data, because size changes don't necessarily directly correlate to changes in strength and injury risk. So this is where the other half of my kind of expertise comes in as an engineer, a biomedical engineer. What I can do is take the imaging analysis one step further and look at the holistic changes in vertebral strength and injury risk. And to do this, we use a model called the Global Human Body Models Consortium. And this was developed as an international collaboration between automobile makers, government agencies like the National Traffic Highway Safety Administration, as well as academic institutes that are working together to improve these models for car crash simulations. So you guys may have heard of crash dummies, which are frequently used in car crash simulations to test how safe the cars are. Well, those dummies are expensive, they have a finite life cycle, and also they're not very representative of actual human responses. So that's where these models come into play. They're highly biofidelic, and they're very detailed, containing over 400 individual physiologically modeled components. This is everything from the bones, to the organs, to the soft tissues, and the muscles. And because of that, these models are extremely representative of what we would expect when human bodies undergo mechanical loads, and they've been used extensively and been extensively validated to improve vehicle safety. So just to show you guys an example of how these models are actually used, on the left you can see an example of the model being run in a frontal car crash situation. So the airbag is deployed, and then the model then makes impact with the airbag. So we can sort of see a lot of the compressive forces in the soft tissues, and it gives us a really good idea of what's going on in the models. And on the right is actually the same human body model, the same simulation, but we're actually looking at how I can extract metrics of stress and strain from these. So you can see that right when it's impacting the seatbelt and the seatbelt tightens, we get areas of red right near the top ribs, and that's where we might actually expect fracture to occur. And so that's how I use these models to get a better idea of what happens with the injury. And so to put this together and how we actually do this with Spaceflight, so I take the imaging portion of the study, which I told you I collect metrics of bone health and muscle health. I can then integrate those into these computational models so that we have models that are customized to each of the 9 crew members in pre-flight and post-flight. I can then run simulations of like a representative loading situation the crew members may experience. So this may be launch, it may be landing, it may be mission abort. In this case, it's a simulation of a capsule landing upside down, which is why you're seeing the astronaut move up into the seatbelt. And then from these simulations, I can then extract out stresses and strains, which we use to calculate injury risk. So since all of these models are customized to each of the individual astronauts, there are a series of steps that we have to do to create this customization for each of them. So first we have model morphing, which means if you imagine that the original FE model is a bunch of points in space, which we call point clouds, we can superimpose all of those points onto the points of each of the 9 astronauts, and then we wrap them around and get them as close as possible so that our original FE model is as close to the original subject geometry as we can get. And then for the bones, I've told you we collect cortical thickness, and that's not a uniform value throughout the bone. So we can actually then map the individual areas, the individual cortical thicknesses throughout regional areas of the finite element model, which gives us a distribution of cortical thicknesses, which is more representative of what we might actually see in the human body. And then for material properties, we can edit things like the elastic modulus for the bone and the muscle, as well as muscle size. You can see in the bottom there, so now we're in the third thing over to the right, and the bottom is the FE model where you can actually see the red beams. Those are where the muscles are modeled as beams. So I can change the size of those muscles, and I can change the thickness of those muscles. And then lastly, we have the simulations that we run. And so those can be either simulations of isolated areas, like just one vertebral body, or it could be a full human body simulation like I showed you on the previous slide. And we do that for each of the 9 astronauts to make sure that the models are customized to each one of them pre and post-flight. And then with that, after we run the simulations, we have actually mechanical sensors, accelerometers, that are embedded in different parts of the model, and that allows us to extract forces and moments and positions of the different pieces of the model, which then we can use to calculate vertebral strength and injury risk. And with this data, we can then make predictions if we know what happens in 6 to 12-month missions, what's going to happen on longer duration missions. So really creating these models and these frameworks are sort of setting up a way for us to make better predictions for interstellar missions. And then with that, I detail a lot about how biomedical engineering can be used to detect and predict bone changes, but what's currently being done to prevent these losses. So other slides aren't advancing quite like I expect. So this is, just to back up and tell you what I was saying out loud, so these are the accelerometers that are on each of the bones that then can extract forces, moments, and positions. And then in terms of what exists now on the International Space Station, so they basically have a suite of specialized exercise equipment up there. They have their own gym that they all use for over 2 hours a day under the guidance of exercise physiologists back on Earth. So one of those devices is called the Advanced Resistive Exercise Device. This provides up to 600 pounds of force and works out all major muscle groups. That's on the far right of your screen. There's also a stationary cycle that they can use, as well as a treadmill that has actually has elastic straps holding them down onto the treadmill to provide normal loading like they would have back on Earth. And while these exercises have been shown to help slow the decline in bones and muscle changes on the International Space Station, they don't completely eliminate the changes. So we still have work to do in this field. So looking towards the future, there are several advancements in countermeasures which, alongside regular exercise, may help us maintain crew member strength during these interstellar missions. They may be the key to helping us get there. So one of the things that NASA and the European Space Agency are working on right now is a compression skin suit. And this uses strips of lightweight plastic material that creates a pressure loading system, providing an additional 1 g of force on the bones and muscles in the body. And this helps add back the effect of terrestrial gravity as they're up on the International Space Station or as they're floating on their spacecrafts. The second thing, which we'll hear more about this afternoon and later in the conference, is artificial gravity. There's currently some bed rest studies that NASA and the European Space Agency are conducting, in which the participants are spun around on a short arm centrifuge on a regular basis to assess whether artificial gravity may be a way that we can prevent these changes. And then just to clarify, this specific study is not looking at like them spinning constantly, but having regular intervals of them kind of having like sessions where they spin to help normalize the physiology and prevent those bone and muscle changes. Then the last thing that I've highlighted is a robotic exoskeleton, which I think is super cool. So the suit was originally designed to help provide extra power for surface exploration missions to the astronauts, but it turns out that they've been used for other creative ways to help exercise measures. So if the astronauts or the crew members were to wear these suits while they were doing their actual exercises, the suit could provide extra resistance in the joints, which would make the exercises more difficult over time. And it could also collect biomechanics data and record that and provide that for doctors and physiologists to actually see if the crew members are doing their exercises properly in a way that best preserves their bones and muscles. So with that, as I wrap up this talk, there are two key things that I want you to take away from what I've been telling you about. Spine strength and injury risk are important to consider because they directly influence long-term crew member performance. And tools in biomedical engineering, such as the imaging analysis where I collected bone and muscle changes, as well as the finite element modeling where I was able to integrate those changes, these can offer clues to how these changes may affect injury risk and spinal strength and long durations. So we must effectively continue to invest in understanding how these bones and muscles change on shorter duration missions before we're actually ready for interstellar travel. So even though the talk and the study that I'm working on is not directly in interstellar, like right now, it's a key step to getting us there. And so with that, thank you all for listening to me right before the break, and I really want to thank my advisor, Ashley Weaver, today for letting me come here and talk to you all, as well as Dr. Rob Hansen, who was my professor in scientific communication last summer and kind of made it possible for me, along with the entire TVIW crew, for me to come and tell you about biomedical engineering. So I really appreciate that and have enjoyed speaking with you all.
I could ask you questions for an hour, but I'll limit myself to two things. Other kinds of remediation, such as biophosphates, salmon calcitonin, maybe more exotic drugs, and also vibration. Mm-hmm. Have any of those been discussed?
Yeah, so bisphosphonates, which is like an osteoporosis drug, that's been used currently on the International Space Station. There have already been like several years of studies looking at how these osteoporotic drugs can be used both before spaceflight and then continuing into spaceflight to help prevent the bone loss. So for those of you that are not familiar with the bisphosphonate, the way it works is it actually prevents bone resorption. So it keeps the bone from... Supposedly, yes. So it's supposed to keep the bone from eating itself faster than it can rebuild itself back up. Yeah, so that's currently being studied right now. And there's a group at Harvard, MIT that are sort of leading that. I don't know as much about that, but it is integrated into a lot of the upcoming exercise equipment on the International Space Station. So you should see more of that soon.
Does the same detrimental effect happens to an astronaut who is forced to swim in a liquid? Because the astronaut need to survive in a high radiation environment, acceleration and deceleration, and many other factors. But as far as the astronaut is swimming in a liquid, this kind of problem will become much negligible. It's my opinion, but I'm not sure that's correct or not.
Are you asking if these changes occur if the astronauts were like swimming?
Yeah.
Okay, so to an extent, yes, because the bones and muscles are not being used, but there are some pieces of the effects of microgravity that are actually affecting like metabolism and core like cellular processes, and that's not going to happen when they're just swimming. There's some pieces of this that we don't understand about how it affects on the cellular level. So yes, we could get some idea of it, but for these very long-term changes, we're seeing like changes in the DNA and we're seeing changes in cellular processes. We couldn't replicate that here by using water.
Okay, thank you.
I know this is a bit more exotic than most of the things you guys are looking at now. I really the skin suit proposal. I think that one's going to be fantastic, but that's just me. This is more exotic and down the road, but have there been any hypotheses about the manipulation of osteoblast and osteoclast activity for controlling skeletal degeneration and regeneration?
Yes, definitely. There are a lot of like upcoming drugs and agents that are being used to help suppress osteoclast activity and then promote osteoblast activity. Yeah, so a lot of those, you're not seeing a lot of it yet because there are a lot of side effects that we're not able to control, and that's why we're not seeing, because if they were working, we'd also see them in osteoporosis, right? So I think, and that's actually going to hopefully drive a lot of what we see, is the research towards osteoporosis is going to help us get to what we need for space travel and getting those figured out. But yes, that's a great question, and it's coming. I've seen a lot of stuff about it, yeah.
We see a lot of things in the news right now where people are starting to actually 3D print muscles and bones and such like that. Do you know of any future experiments that look into 3D printing on the ISS and actually specifically looking at those types of degradations from looking at sort of a small scale? You can actually do in situ testing on board the ISS.
That's a great point. I'm not aware of it, but I think bioprinting could have a lot of potential to sort of show us these changes in the long duration, right? Because we can't measure changes when astronauts are only there for 6 to 12 months. So what you've presented would be a great way to look at multi-year effects, but I'm not aware of anything that's happening yet.
We've been told over, decades that centrifugal artificial gravity is the solution to all of these problems. Has anyone ever done any actual studies on that to see if, in fact, centrifugal gravity is exactly the same on a musculoskeletal system and other soft tissue systems as normal gravity?
That's another great question. So the European Space Agency and NASA are both currently running a 60-day bed rest study to look at the changes using a short arm centrifuge over in Germany. So they're actually spinning them at regular intervals, and like that, the results haven't been released yet. So maybe we're going to know more soon about the effects, but not currently. We haven't seen really large studies yet.
Well, let's thank our speaker again.